In this video, we will look into gas turbine example. Consider the flow of combustion gases with gamma equal 4 over 3 and R equal 287 joule per kilogram Kelvin through a normal turbine stage such that the flow angle at the exit of the rotor is the same as that entering the stator, and alpha 1 equal alpha 3 equal minus 14.4 degrees. The inlet total temperature is T01 equal 1200 K. The axial velocity is constant, which equal 280 meter per second. The flow leaves the stator at angle alpha 2 equal 57.7 degrees. The mean radius of the rotor is equal 17 centimeters and the rotor turns at 20,000 rpm. A. Find the work done and the drop in stagnation temperature across the stage. B. Determine the flow angles of the relative velocity at the inlet and exit of the rotor. C. Calculate the contribution of internal energy and flow work in increasing the kinetic energy through the stator. And D. Calculate the contributions of internal energy, flow work, and kinetic energy to work delivered by the stage. Before we solve this problem, it's a good practice to highlight the information that we can get from the question. First one is the uh, gamma equal 4 over 3 and the gas constant R equal 287 joule per kilogram Kelvin. And then the angle alpha 1 is equal alpha 2 alpha 3, which equal minus 14.4 degrees. And T01 or the inlet total temperature is 1200 Kelvin and the axial velocity is constant, equal to 280 meter per second, and the alpha 2 is equal 57.7 degrees. The radius or the mean radius of the rotor is equal to 17 centimeters and the rotor turns at 20,000 rpm. That is all information that we can extract from question, which is important in order to solve the question. Okay, first of all, what we have to do is to sketch the velocity triangles for the turbine. The velocity triangle for the turbine we have at the inlet of the stator, at the outlet of the stator, which is equal the inlet of the rotor, and at the outlet of the rotor. So we have condition number 1 is at the inlet of stator. Condition number 2 is at the outlet of the stator, which equal the inlet of the rotor. And condition number 3 is at the outlet of the rotor. Work delivered by the turbine can be calculated using this equation. W equal U VU2 minus VU3. In this equation, in order to solve this equation, we need to know U, the blade speed, VU2 and VU3, which are not given in the question. So we have to find this value first before we can solve work delivered by the turbine. So first we have to find the blade velocity. Blade velocity can be calculated using this equation. U equal r omega. Okay. Omega is the angular velocity and u is linear velocity. We know from the question the value of r and the RPM, or the rotation per minute of the turbine. So we can use that information in order to solve u. Okay, so u is equal to r 0.17 multiplied by the RPM of, or the rotation per minute of the turbine, which is 20,000, and this is the conversion factor to convert the unit into meter per second. So now we have the value of u, which equal 356.0 meter per second. Next, the tangential component of the absolute velocity leaving the stator, which is the VU2. From velocity triangle, we can calculate VU2 equal Vx tangent alpha 2. So we have the Vx value and alpha 2 value. We can just straight away put those values in this equation to get VU2 equal 442.9 meter per second. Next, the tangential component of the absolute velocity leaving the rotor, which is VU3. Because at the exits of the rotor for a normal stage, alpha 3 equal alpha 1, or the angle at the exit of the rotor is equal of the angle of the inlet of the stator. And we can calculate VU3 equal Vx tangent alpha 3. So we have Vx value and alpha 3 value. So we plug in those values inside this equation. We will get VU3 equal minus 71.9 meter per second. Please be careful about the negative and positive sign in this equation. Okay, now we have VU value, the value of U, the value of VU2 and VU3. So we plug in those values inside work equation here. We will get the work delivered by the turbine equal to 183.3 kilojoule per kilogram. And next we want to calculate the temperature. The stagnation temperature drop across the rotor is given by this equation, which is delta T0 equal the work delivered by turbine over Cp. We just calculated the work delivered by turbine, but we don't have Cp value. But from question, we can calculate Cp value using this equation. Cp equal gamma r over gamma minus 1. We have gamma equal 4 over 3 and r value given in the question. So we just plug in those value inside this equation. We will get Cp equal 1148 joule per kilogram Kelvin. We plug in this value inside this equation. We will get delta T0 equal 159.7 Kelvin. Alright, next we want to solve question B, which is the flow angle of the relative velocity at the rotor inlet. Which is, if we look into this rotor inlet, in this velocity triangle, the rotor inlet angle is beta 2. Beta 2 can be calculated using this equation. from trigonometry. If you apply trigonometry at this velocity triangle at the inlet of the rotor, we know that beta 2 can be calculated using inverse tangent WU2 over WX. Here we don't have the value of WU2, but we already know Wx is the axial velocity, which is constant throughout the turbine. Okay, now before we can get beta 2, we have to calculate WU2, which is the tangential component of the relative velocity at the rotor inlet. Can be calculated using this equation. WU2 equal VU2 minus U. We have known, or we have calculated VU2 and U previously, so we just plug in those values inside this equation. We will get WU2 equal 86.9 meter per second, and then we just plug in this value inside beta 2 value. We will get beta 2 equal 17.2 degrees. Next, we want to calculate the angle of the relative velocity at the exit of the rotor. Looking at this uh, velocity triangle, we know that the angle of the relative velocity at the exit of the rotor is beta 3. Beta 3 can be calculated using this equation, which equal to inverse tangent WU3 over WX. We know WX is constant, and we already know the value of WX, or the axial velocity, from the equation. Here we don't know WU3, so we have to calculate WU3 first, which is the tangential component at the exit of the rotor. Can be calculated using WU3 equal VU3 minus U. And we already know the value of VU3 and U. We plug in those values inside this equation. We will get WU3 equal minus 427.9 meter per second. Now we can solve beta 3. We just plug in this value inside beta 3 equation. We will get beta 3 equal minus 56.8 degrees. So we solve question B. Next, we want to look in. Next, we want to solve question C, which the contribution of internal energy and flow work through the stator. First, we want to calculate the internal energy through the stator. Internal energy through the stator, which is the U1 minus U2, we can calculate using CV T1 minus T2. Here we don't have the information of CV T1 and T2, so we have to calculate these three values first before we can get the value of internal energy through the stator. So what we have to do first is to get the value of CV. CV can be calculated using this equation. CV equals CP minus R. We have calculated CP. We have calculated CP previously, and R is given in the question. So we just plug in those value. We will get CV equal 861 joule per kilogram Kelvin. And next we want to calculate T1, which is at the inlet to the stator. The static temperature is given by T1 equal T01 minus V1 squared over 2CP. So here, in order to solve T1, we need V1. Okay, V1. In order to calculate V1, we know that the axial velocity is constant, Vx. And at the exit of the rotor, for a normal stage, alpha 3 is equal alpha 1. So we can calculate V1 if we know V3, because V1 is equal to V3. So V3 equal square root of Vx squared plus Vu3 squared. So we have the value of Vx, which is the axial velocity from the question. Vu3 we have calculated previously. So we would just plug in Vx and Vu3 values inside this equation. We will get V1, which equal V3, equal 289.1 meter per second. So we can solve T1 because now we have V1 values. We have T01 from question and Cp we have calculated previously. We plug in those values inside this equation. We will get T1 equal 1163.6 Kelvin. Okay, next we want to know T2, which the static temperature at the exit of the stator. T2 can be calculated using this equation. T2 equal T02 minus V2 squared over 2Cp. And we have known all these values either from question or from what we have calculated previously. So we just plug in those values inside T2 equation here. We will get T2 equal 1080.4 Kelvin. So now we can solve the internal energy through the stator by plug in these values inside the internal energy equation here. So we will get the internal energy through the stator is equal to 71.6 kilojoule per kilogram. Next, we want to calculate the flow work through the stator. The flow work through the stator can be calculated using this equation, which is P1V1 minus P2V2 equal R T1 minus T2. So we don't have any information of this, so we can calculate, but we have T1 and T2, which we just calculated previously, and R is given in question. So we just plug in those values inside this flow work equation. We will get the flow work through the stator is equal to 23.9 kilojoule per kilogram. We also want some time to calculate the kinetic energy. So the increase in the kinetic energy across the stator is actually can be calculated using this kinetic energy equation. Half V2 squared minus half V1 squared. So we know V2 and we know V1. So we just plug in these two values. We will get the increase in the kinetic energy across the stator is equal 95.5 kilojoule per kilogram. This value is actually the sum of the previous two terms, which is the flow work and the internal energy. So now we know that how much internal energy contribute to the increase in kinetic energy across the stator. We can do it in terms of percentage. Alright, next we want to solve for the last question. We want to know the internal energy, flow work and kinetic energy across the rotor. Similar to what we have done previously, we want to calculate the internal energy using the internal energy equation, which is U2 minus U3 equal to CV T2 minus T3. In this question, we don't know T3, which is the static temperature at the outlet of the rotor. We can calculate T3 using this equation. T3 equal T03 minus V3 squared over 2Cp. Here we know V3 and Cp, but we don't know T03. Since the stagnation temperature drop across the rotor is delta T0 equal 159.7 Kelvin, which is given in the question, the stagnation temperature after the rotor, which is T03, can be calculated using T03 equal T02 minus delta T0, which equal, we know T02 from previous calculation, 1200 minus delta T0, 159.7. We get T03 equal to 1040.3 Kelvin. So now we can solve the internal energy, or no, the T3 or the static temperature at the outlet of the rotor by plugging in these values inside this equation. We will get T3 equal 1003.9 Kelvin. So now we can solve the internal energy by plug in T3 value that we just calculated here, and T2 and CV we have calculated previously. We will get the internal energy across the rotor is equal to 65.8 kilojoule per Kelvin. Next, we want to look into the flow work across the rotor. Similar to the previous or to the calculation at the stator, the equation is very similar but using different uh, uh, position. For the rotor, we use P2 V2 minus P3 V3, which equal RT2 minus T3. Here now we know all the information needed to solve flow work. So we just plug in those values. We will get flow work across the rotor is equal to 21.9 kilojoule per kilogram. And finally, the kinetic energy. In a normal stage, the increase in kinetic energy across the stator is equal to its decrease across the rotor. Hence, the decrease in kinetic energy across the rotor is, if we want to calculate, we can calculate using this equation. But because it is actually equal to the decrease or to the increase across the stator, so we already calculate the increase, the kinetic energy increase across the stator, which is the value is equal to 95.5 kilojoule per kilogram. Okay, in this at the rotor, similar to the at the stator, which is um, the sum of internal energy and flow work will equal the decrease across the rotor, or the decrease in kinetic energy across the rotor. Now we have solved this example. I hope you can understand uh, more on how to solve gas turbine problem. Thank you. See you in next video.